It's probably fair to say that at some point we've all sat around a campfire watching the flames flicker back and forth. And you may have even wondered, well, what are the flames actually made of? And beyond that, you may have even thought, well, how about fireworks? Why are they all different colours? Or gas torches? Or even green flames coming out of manhole covers? Well, you're in luck, because in this video, we're going to have a look at what flames actually are and what they're made of, and why some flames come in different colours depending on what is being burnt. So that the next time you're sitting around a campfire, you can wow your mates with your amazing fire behaviour knowledge, and I bet they'll all be very impressed.
Okay, so as we get started, it is worth noting that this can be quite a technical subject. And in fact, years ago, when people were trying to define some of these reactions, that became the birthplace of quantum physics. Now, I've said it before, I'm a firefighter, not a scientist, so I am going to try and keep things relatively simple, while still maintaining accuracy as I go. But if you're looking for quotes for your PhD, probably try and find something a little bit more robust than this video. But if you're just interested in how fire works, I think that this is a pretty good representation. Now, when we're talking about fire, if I were to ask you to think about a flame, what you will think about is most likely dependent on your previous experiences. Because if you're a firefighter, then you might think about a building fire with flames starting to roll the ceiling. Or you might even think about a car fire or even a bushfire moving across the landscape. Whereas if you haven't been a firefighter before, you might be more likely to think about a bonfire or a wood heater or even just a simple candle. Now, the interesting thing is that all of these examples are examples of one kind of flame, being a diffusion flame. Now, a diffusion flame occurs when the fuel and air mix at the moment of combustion. Now, this is an important concept because if you can understand how a diffusion flame works, then that's going to go a really long way to understanding how all of these different flames work. So, we're going to take a look at one diffusion flame in particular, being a candle. I know, it's not very exciting, but the really cool thing about a candle is all the pieces are really easy to identify in a controlled situation. And if we were to think about the fire triangle in relation to our candle, the fuel is the wax itself, and the wax is a hydrocarbon known as paraffin wax. And what it is a whole heap of hydrogen and carbon linked together in big long molecular chains to form a solid fuel source. Now, if you've been watching this channel, you'll know that we're going to need to turn that into a gas later on, but for now, we'll focus on the other two elements, being oxygen and heat. Now, the oxygen comes from the air that we're currently breathing, where there's around about 20.9% oxygen. Now, the rest of it is made up of nitrogen and some other minor gases, but it's the oxygen in the air that's the important part that we're focusing on, because it's the oxygen in the air that will combine with our fuel source later that gives us our chemical reaction. Now, the heat in our case comes from a piloted ignition, because as you can see, I light my candle with a match, and this gives the candle that initial energy it needed to turn the wax from a solid into a liquid and then into a gas. Now, when we look closer at the flame, we can start to unpack what's happening inside the flame, because we know that the wax is being melted and then drawn up the wick by capillary action. When it gets drawn up the wick, it then gets exposed to more heat. Now, when this wax, which is hydrocarbons, gets exposed to more heat, it then gets released as a gas, and all of these hydrocarbons start floating away from the wick. But inside the flame, it's almost all fuel. There's very little oxygen inside there. And so our fuel needs to keep moving away from the wick further to the outside of the flame before it is finally exposed to a lot of oxygen. Now, what we call this area of the flame is the reaction zone, because this is where our fuel source is combining with oxygen to form new products. For example, when the hydrogen joins with the oxygen, it forms H2O, or water. And it may come as a bit of a surprise, but water is a very common byproduct of fires that we encounter, because hydrogen is also a very common fuel source. Now, the other component is carbon, and if this is fully oxidized, it will form carbon dioxide. And if the combustion isn't very efficient, it can form carbon monoxide, or simply traverse through the reaction zone completely without ever being oxidized and being released as carbon, or what we see as black smoke. Now, when these reactions are happening, when the hydrogen is turning into H2O and when the carbon is turning into carbon dioxide, there is a lot of energy being released. And this energy is released as heat in all directions, meaning that if we put our hand near the candle, we will be able to feel the warmth from that candle. But in a similar way, that heat is also going back towards the wick, where it allows our self-sustaining chemical reaction to occur, because as more heat is being emitted towards the wick, more liquid wax is being turned into a gas, where it can then float away from the wick into the reaction zone where more heat is produced. That heat radiates back towards the wick, and the whole process continues in a big chemical chain reaction. And this is what we're talking about when we mention the fire tetrahedron. It's a mixture of heat, fuel, oxygen, and a chemical chain reaction. And this is how this chemical chain reaction works. The fuel floats away from our fuel source, it joins with the oxygen from the air, which is how diffusion flames work. That then creates a lot of heat. That heat is radiated out in all directions, including back towards our fuel source, where it then allows more fuel to be released, and this whole chemical chain reaction can continue. Okay, so that provides a reasonably simplified take on combustion, because it is a lot more complicated than that, but for the purposes of today's video, I think that's sufficient. Now, we still haven't talked about what the actual flames are. What are we looking at when we're looking at the yellow, orange, and red flames? Well, we've kind of already hinted at it, because as we're turning our hydrocarbons into a gas, they start floating away from the wick. Now, this means that there's a lot of carbon inside that flame. Now, that carbon is also being exposed to the heat being created by the reaction zone. And what we begin to see now is something called black body radiation. Now, this is where we need to quickly pause and talk about the electromagnetic spectrum, because this plays a really big part in how flames will appear. When we're looking at light, what we're looking at is electromagnetic radiation that our eyes collect and then interpret as light. But this is only accounting for a very small part of the overall electromagnetic spectrum. And if we look below the visible light spectrum, we will see infrared energy as well as microwaves and radio waves. But if we look above the visible light spectrum, we will see ultraviolet radiation as well as gamma rays and other radiation. Now, the reason why all of this is important is because the next thing we need to talk about is black body radiation. Because as our hydrocarbons are floating away from the wick, they're being exposed to all of that heat from the reaction zone. This means that the carbon contained within the flame is going to begin to heat up. If we heat it a little bit, it will start to emit electromagnetic radiation in the infrared zone, which means that our eyes won't be able to see it, but if we had a thermal imaging camera, it would be very clear to see. But if we continue to heat that carbon more and more, eventually it's going to start to move into the visible light spectrum at a dim red. Now, this is where our eyes will start to be able to see the light coming from the flame. And as that flame gets hotter and hotter, it will eventually become a bright red, an orange, and even become a yellow. And so this explains what we're looking at when we see a flame. Essentially, what we're seeing is carbon being heated to the point where it starts to emit electromagnetic radiation in the visible light spectrum. And this is what our eyes are interpreting as a flame. Now, the really cool thing about this is that when we're seeing flames, we can start to approximately determine their temperature based on those colours. And that can even be helpful on the fireground, because if we see flames that are inside a building and they're only a dim red, we know that those flames aren't as hot as they could be for one reason or the other. Now, the chances are is it because that they will be burning in a ventilation controlled state, meaning that the combustion isn't as efficient as it could be. And therefore, it's quite possible that if we see red flames and we give that fire more oxygen, then the combustion could then become more complete, and as a result, the flame temperature could rise. Now, the other really interesting thing about all of this is that it's consistent regardless of the flame size. Now, this means that while the temperatures of the flames inside a structure fire may reach 1,000 degrees centigrade, the same thing can be said for a candle sitting on the bench, because these flames are effectively operating in the same way, because they're both burning hydrocarbons. In the case of a structure fire, we might be looking at polyurethane foams, which is a combination of hydrogen and carbon, or natural materials like timber, which is also a combination of hydrogen and carbon, but there is also some oxygen and various other things mixed in there. But the main building blocks are still the same between our candle and our structure fire. And the same thing can be said for bushfires and car fires. Yes, there are some other materials, but a lot of the things that we're seeing in the flames is carbon emitting this black body radiation. The really interesting thing about this is that while the structure fire might be reaching 1,000 degrees centigrade, so is my candle. And so when you see reports on the news that say that firefighters had to withdraw because the temperatures were reaching 1,000 degrees centigrade, well, to be honest, I could argue the same thing for when I have a candle alight in the room, because the temperatures are reaching 1,000 degrees centigrade. It's just that the heat release rate is much, much lower for a candle than it is a structure fire. But that's a bit of a segue. We'll get back to flames. So now we've seen that when we're looking at orange and yellow and red flames, because of the sheer abundance of carbon on our planet, chances are what we're looking at is carbon being heated to the point where it starts to emit electromagnetic radiation in the visible light spectrum. And that's what flames actually are, is very, very hot carbon or soot that hasn't been through that reaction zone yet, because once it goes into that reaction zone, it will then turn into carbon dioxide or carbon monoxide, depending on the combustion. But that's what flames actually are, is they're the products of pyrolysis or vaporization that haven't been through that reaction zone yet and are simply being heated to the point where they start to emit light. But that only accounts for diffusion flames, because we still haven't talked about where blue flames, for instance, the blue flame you'll get out of a Bunsen burner, come from. Because I can take a diffusion flame with a nice yellow flame, turn the aperture, and then get a bright blue flame. Now, I haven't changed the fuel source. All I've done is changed how that fuel and oxygen are mixing, and this is what's known as a pre-mixed flame. Now, what's happening here is very interesting, because it's not just a change in colour. There is actually a significant change in the combustion that is occurring here, because now, as the oxygen and the fuel travel up the Bunsen burner, they're mixing into their ideal mixture, which means that for every bit of hydrogen or every bit of carbon that is being supplied as our fuel source, there is the right amount of oxygen sitting around that fuel ready to fully oxidize those fuels. Now, this means that when the fuel comes out of the end of the Bunsen burner and begins to burn, most of our fuel is fully oxidized almost straight away, meaning that we now have a very efficient flame, which as a result reaches much higher temperatures than the diffusion flame can. But now, as a trade-off, we now no longer have all of that soot in the flame that we needed to produce that black body radiation, which means that we can't produce those orange and yellow and red flames anymore because there simply isn't that carbon available to emit that radiation. So now, instead of seeing those orange and yellow and red flames, what we're getting instead is a completely different process known as molecular emission. Now, as I found in trying to make this video, molecular emission is quite complex, so I'm just going to provide a fairly simplified version of it now. So if we have a look at some of the products in that flame, you'll get molecules that are being exposed to large amounts of heat. Now, when these molecules are being exposed to large amounts of heat, their electrons can jump to a higher state of energy to compensate for that additional energy coming in. But that doesn't last for very long, and the electrons want to jump back down to their previous state. Now, because of the laws of thermodynamics, energy cannot be created or destroyed. It can only be transformed, which means that when we're dropping back down to a lower energy state, we need to somehow get rid of that energy so that the electrons can drop back down. And the way that that happens is that a photon of light is produced as it drops back down from the higher state of energy to the lower.
And in the case of our Bunsen burner, the light that is produced is predominantly due to these two molecules. And when we have a look at this graph, we can see that the majority of the light that is being produced by these molecules is from the blue area of the visible light spectrum. Now, the interesting thing is that this blue light is a reflection of what energy level the electron is dropping back down from when it reached its excited state. And therefore, molecular emission occurs over specific bands rather than an entire spectrum, as we see in blackbody radiation. And this brings us to a couple of interesting points about how molecular emission is different to blackbody radiation. Because in blackbody radiation, we can estimate the temperature of the flames based on the color, where cooler flames are red in appearance, and as they get hotter, they transition through orange and then to yellow. Whereas with molecular emission, the color doesn't change over a broad spectrum like it does with blackbody radiation. Rather, it is produced in distinctive bands in relation to the excitement of the molecule's electrons. In fact, I can even demonstrate this with a simple experiment, but before I get started, please don't pay too much attention to the exact temperatures shown by this device because, as you will see soon, this device was in no way designed to be exposed to the kind of temperatures that I'm exposing it to. So maybe just think of the temperatures as more of a proof of concept rather than the exact temperatures that are being experienced in the flame. If I take a temperature reading from the premixed flame of the Bunsen burner, it will be much hotter than the diffusion flame from the Bunsen burner. Now, I played around with the Bunsen burner a little bit, and this was the highest temperature I was able to get out of that flame. But when I turn the Bunsen burner off and fire up a gas torch, I was able to get a temperature jump by more than 100 degrees Celsius with a very similar blue flame. And if that wasn't enough, I broke out my small welding torch, and for the very few seconds that the thermocouple held together before it finally melted, you can see that it really spiked the temperature by many hundreds of degrees, despite still having a very similar blue-looking flame. And so this just demonstrates that it's very different to blackbody radiation, where that can operate over an entire spectrum of colors, from the infrared all the way through the visible light spectrum. Molecular emission will only emit photons in specific bands, depending on what molecules are present in the flame and what level of excitement they are dropping back down from.
Okay, so that accounts for our blue flames, but that doesn't account for all the different colors in fireworks or even green flames coming out of manhole covers. Now, to talk about them, we need to talk about a thing called atomic emission, which is in some ways quite similar to molecular emission, but there are some key differences because when we're talking about atomic emission, we're seeing those electrons jump to that higher state of energy in response to more heat coming in. And in a similar way, when they drop back down to their original energy state, they will emit photons of light in a specific band of energy. But the difference with atomic emission is that because we're talking about individual atoms rather than entire molecules, now what we see is a very narrow band of light. And this is actually quite helpful because the band of light that will be produced by this atomic emission is completely reliant on the original atoms that are being heated. For example, copper atoms, when they are heated, they can produce photons in a distinct green band, which is quite likely what we're seeing in the case of the green flames coming out of the manhole cover. And when it comes to fireworks, it's a similar thing. They add different products like barium, sodium, and copper to the fireworks to make all of the different colours. Now, the really cool thing is that this process is actually quite similar to some other processes that we see. For instance, auroras, where high energy particles from the sun collide with oxygen and nitrogen in Earth's upper atmosphere, which then excites these atoms. And then when they drop back down to a lower state of energy, they emit light.
So, I'm probably out of focus, but that's because I'm focused on the sky. This is a video. Yep. So, video of auroras in Tasmania. Since when was that a thing?
So yeah, that's pretty cool in that when we're seeing fireworks or green flames coming out of manhole covers, what we're seeing is a fairly similar process to what happens when we're seeing auroras light up the night sky. And so there we have it. When we're looking at orange and yellow and red flames, what we're seeing is a lot of soot being heated to the point where it starts to emit this black body radiation in the visible light spectrum. When we're seeing these blue flames, what we're seeing is molecular emission. So we're seeing molecules being heated to the point where the electrons of molecules can jump to a higher state of energy, and when they drop back down, they will emit photons as a result. And when we're seeing fireworks, what we're seeing is atomic emissions. So we're seeing individual atoms and electrons jumping to a higher state of energy, and when they drop back down, they emit that visible light. All right, so there we go. Flames are an incredible mix of chemistry and physics, and this is a really simplified version of all of those processes going on. But hopefully I've been able to stay pretty true to the actual processes and haven't wavered too much. But this is just a bit of an intro. Hopefully it's been helpful. Hopefully you enjoyed it. If you liked the video, give it a like. If you've got anything to add, chuck it in the comments down below. I do appreciate all your feedback. If you've got any ideas or things you want me to talk about in future videos, chuck it down there too. Who knows, I might go ahead and make it. Yeah, thanks for watching. I'll catch you in the next one. Cheers.